third session of the day, latest trends in 5G and 6G. It's my pleasure to introduce our resource person, Dr. Debda Kandar, for the session of this 5-day FDP program, 5G Antenna Design Engineering, organized by Mailam Engineering College, sponsored by AICTE Training and Learning Academy, ATAL. Our chief guest has completed his MTech Information Technology, a PhD in Engineering in Jadwar University, and postdoctorate in University of Johannesburg. His area of interest includes artificial intelligence, soft computing, machine learning, wireless communication, radar imaging. He has more than 20 years of professional experience, currently holding the post of Associate Professor in the Department of Information Technology, Northeastern Hill University, Shillong, India. Our chief guest possesses a strong publication history and has published many papers in international journals and conferences. He has authored more than 7 book chapters, and I'm very proud to say our chief guest has received Young Scientist Award from Union Radio Science International at Vijayan Vahan, Delhi, for this research work. President of India, at which Dr. APJ Abdul Kalam invited him at his residence on that occasion. We are very happy to have you with us, sir. Now I request our chief guest to take over the proceedings.
Okay, thank you for a brief introduction, and good afternoon all the participants joining today. And let me give my thank to Mailam Engineering College, as well as the coordinator Dr. S. Ganesan and Dr. Sugonna. Thank you for inviting me, and let's start our discussion. So can you see my screen?
Yes, sir.
Okay. So is it visible?
Yes, it's visible, sir.
Okay. So let's start our discussion today. And it is 5G and beyond wireless technology. Instead of 6G, I have mentioned 5G and beyond. And myself, Dr. Debda Kandar, Associate Professor, Department of Information Technology, Northeastern Hill University, Shillong, Meghalaya, India. And actually, the most of the PPTs or content I have taken from one of my collaborator, Dr. Emil Johnson, Associate Professor and Docent.
Sorry to interrupt you, sir.
Hello.
Sorry to interrupt you, sir.
Yes.
Yes, it would be great if you could make your slide as a full view, sir, so that.
So it is full view.
Yeah, just give me 1 minute, sir. So could you change your slide, sir? We could just see a blank screen here.
Is it visible?
Yeah, we could be able to see a blue screen over here, but we're not able to see the slide.
Oh, why it is paused? It is showing paused. Is it visible now?
Yes. Actually, just click that resume slideshow, sir.
Is it visible?
Yeah, it's visible, sir. Just it's in the slide mode. Actually, we need to see the slide in the slideshow. Yes, just click that, sir. Resume slideshow.
Now it is in slideshow. Is it visible?
Yes, sir. You can proceed, sir. Yes.
Okay. So this is my first slide. So as I mentioned, so contents I have taken few contents from Dr. Emil Bronson, Associate Professor and Docent in Communication Systems. So Linköping University, Sweden. Okay. So today, actually, this is my outline of today's talk. So though it is the faculty development program on antenna systems, but today I'll be talking the importance of antenna systems in today's communication system, basically in 5G and beyond 5G. So outlines are like that: cellular communications. So here I'll discuss about how to improve spectral efficiency. Beamforming is one solution for that, to improve the spectral efficiency. I'll talk little bit about multiple input and multiple output. Then from that MIMO system, we will talk about massive MIMO system. And then we talk about some world record in spectral efficiency. Then we'll discuss again how big we can make the massive MIMO. This is basically called massive MIMO when the number of antennas are huge. So what should be the size of this system? Then we'll claim that massive MIMO is massive in number but not in size. So this is one section we will discuss till 5G, and beyond 5G, I'll try to highlight some of the open research areas, especially in cell-free network, where I'll talk a little bit about radio strip antenna systems. And then I'll talk about some passive reflecting surface, which is nowadays so many names are there, is popularly known as intelligent reflecting surface. And then I'll talk about holographic beamforming. Okay. So let's start about what is wireless communication that you people use your day-to-day life activities with these devices. Basically, it is communication between a transmitter and a receiver. So the device from which you transmit and the device you receive, that is receiver. And basically how it does some transmission of some information. How it can be done? With the help of so many devices, maybe electromagnetic signals, okay, and that is wirelessly. So let me define this device, your mobile phone. Am I audible properly?
Yes, sir. I'm sorry to interrupt you. Actually, your slides are not changing, sir.
No, I did not change.
Okay, fine, sir. Fine.
Only in the second slide.
Yeah, no. Like we are not able to see the second slide, sir. It's still in the first slide itself.
Oh.
I believe you have to click that resume slideshow so that.
Yes. Once I'm clicking on resume share, so it is not showing the full screen.
Yes, sir. I believe it's something related with that your video as well, sir. The PPT and as well as your video is turned on, and that's why I believe we're not able to see the full view mode, sir. We can just try by disabling your camera so that we can see, because morning also we had the same problem, sir.
Is it okay now?
It's okay, but can you try the slideshow now, sir?
Okay, let me check. Is it visible?
Yes, sir. It's visible, but still in the same screen. But not a problem, sir. You can continue.
Which
just
slide
make
it is
sure
showing?
whether slides are changing, sir.
In my screen, it is changing. Like
Okay.
what is wireless communication? That slide, is it showing?
Yes, sir. Can you go to the next slide, sir? Just for check.
I changed already to next slide.
No, no, it's not moving, sir. I would request you to kindly stop screen share and once again share your screen, sir, so that we can rectify this problem.
Okay, okay, okay. So I just stopped screen sharing. Again, I'm sharing my screen. Screen sharing failed to start. Let me try once again. Is my screen visible?
Yes, sir. Yes, it's visible now.
So let me go to full screen. Is it visible now?
Yeah, it's visible, sir. Actually, it's still in the same mode. It's not going to that slideshow mode. That's not a problem, sir. If you can able to change the slides, that's fine. Could you please just go to the next slide, sir?
Can you see?
No, sir. It's still in that what is wireless communication slide, sir.
Now this one.
Yes, now it's okay, sir.
So only problem is I cannot go for this full screen. Once
Yes.
I'm going for full screen, then it is not showing to you.
Yes, sir. Yes, sir. You can continue in this mode, sir. The slides are very clear, sir. Not a problem.
Okay, okay. So in this mode only, let me start. Is it okay?
Yes, sir.
Okay. Okay, so let's start our discussion once again. So I was talking about what is wireless communication. So it is basically communication between two devices, maybe one user and another one maybe base station, or it may be access point. So transmission between one user and base station, and whatever we send, it may be text, image, or sound. Basically, it transmits in the form of zeros and ones. Okay. Now, if we consider the today's communication world, it is very fast traffic growth, because we are not limited to only voice communication, rather of video streaming, social networking, gaming, even so many killer applications are there, and which leads to consume more gigabyte per month. New applications, more consumptions of data. And basically, there is 50% annual increment in data traffic, and which we expect that it will be 1,000 times more till 2034. So to achieve that, we need new technologies, because current today's 5 technology is even not sufficient to support that much of data traffic. So let me present one table which is provided by Ericsson Mobility Report in November 2017, which mentions that in 2016, the people were using on an average 2 devices, whereas in 2021 and 22, it is per person device is 3.6. So more devices and more data traffic every year. 10% more devices, even 47% more traffic. Now, if we consider the second graph, consumption of data in 2016, it is around 970 megabytes per month, which is around 9 GB per month per person in 2020. So considering 10% more devices, there is almost 33% more per device data consumption. Now, how to handle this 1,000 times more data? So we need to improve the capacity of the system, today's wireless communication system. So how we define the capacity of the cellular network. So capacity, it is defined in terms of bits per second per square kilometer, because ultimately in the geographical area we will be defining with some cellular network, and that capacity is defined by bits per second per square kilometer, which is basically product of three factors. One is cell density, spectral efficiency, and available spectrum. So cell density means number of cells per square kilometer. So number of cell means, and today's scenario, normally we consider that one base station or one access point in a cell. So number of cells per square kilometer means number of base stations per square kilometer, which is defining the cell density. So to improve the cell density, we have to improve what? The number of cells, or the number of base stations, or number of access point per square kilometer. The second term, what we call spectral efficiency, and which is defined by bits per second per hertz per cell. So within a cell, so how much data rate will be available for unit spectrum? What does it mean? So any service provider allotted say 10 hertz of spectrum. On using these 10 hertz spectrum, how much data rate can be provided? So that is the measure of the spectral efficiency. And last term is basically available spectrum, and that is measured in hertz. If we increase the spectrum, available spectrum, capacity should be improved. If we increase the cell density, means densify the cell, putting more number of access point, capacity will be improved. And improve the spectral efficiency. So improving spectral efficiency is not a joke. Now, if we multiply all these factors, cells per kilometer and bits per second per hertz per cell and hertz, it will come bits per second per square kilometer. Okay. Now, how do I achieve this 1000 times more increment? Maybe 2030 or 34. So Nokia, they proposed some way out in 2011. What they mentioned, if cell density improved by 10x, means 10 times, spectral efficiency improves 10x, and 10 times more spectrum is available, then we can achieve 1000 times capacity. Whereas SK Telecom in 2012, they mentioned their approach is 56 times densify the cell and spectral efficiency 6 times and 3 times more spectrum. So it come around 1000. So 56 into 6 into 3, most probably 1008. So this way, the 1000 times capacity can be improved. So we also see how we can achieve 1000 times more capacity of the cellular network. Is my screen visible sometimes? Because as video is off, so I'll be communicating to you. So
yes, sir, it is visible, sir.
Okay, good. Now, in current day cellular network, coverage area, so geographical area are divided into small hexagonal cell. So in reality, cell may not be hexagonal, depends on the channel condition. Okay, so in reality, it may be something else from the hexagonal cell, but still let it assume as a theoretical design, it is hexagonal, and each cell having one access point or base station, and which is responsible to provide the service to the user within that cell. So this is the current scenario of cellular network. Now, if we densify by introducing more access point within a cell, so distance should be reduced, also power should be reduced. Now, what should be the challenge then? Interference may increase. Now, how long you can densify? You can densify a little bit more, but you cannot densify like 50 times. 10 times it is acceptable, densifying the cell in reference to the current scenario. Okay. Now, the second factor is the spectral efficiency. So, as we can improve the spectral efficiency, we can improve the capacity of the system. The simplest way to improve the spectral efficiency to increase the power. So, increasing power, listener may be improved and spectral efficiency can be improved. Now, how long? Now, it is one fact that each doubling spectral efficiency requires 70 times more power. So, how much power requires only doubling using this, doubling the spectral efficiency using current scenario? Instead of that, if we introduce the MIMO technology, that is multiple input, multiple output technology, where they can use many number of antennas, and antennas can be used to directly transmit the beam to a particular user. So for this user, maybe this beam will be used. For this user, this beam will be used, and they can use same frequency. Basically, this technology is known as space division multiple access. I'll come in more detail, but today I may not discuss any technical more exploration on that, but I try to give you some idea, and finally I'll try to give some open research area in today's 5G and beyond 5G communication. So this is one of the easiest way introducing MIMO technology. The spectral efficiency can be improved because same frequency can be used for this one, for this user, for this user, for this user. Why? Because this user, as the beams are very narrow, this beam won't be interfering with the next beam. Whereas in the previous current scenario, the single antenna system, it will be illuminating in all directions. Okay, so this is maybe one of the solutions for improving the spectral efficiency. And the third factor, as I mentioned, is more frequency spectrum. More frequency spectrum means maybe bandwidth we also can improve, or maybe higher frequency. So more spectrum reduce time per transmission. Now, are there any unused spectrum? Now, today's, you see, 300 to 5 gigahertz, it is almost occupied by 2G, 3G, 4G, Wi-Fi, TV, military use. So it is almost occupied. Let me take one example in Sweden. So they use 580 megahertz for cellular system and 540 megahertz for Wi-Fi. So both Wi-Fi and cellular system consume almost 1 gigahertz of spectrum. Now, what we propose Nokia or SK Telecom, now if we want to 5 times spectrum, so it is not possible till it is occupied till 5 gigahertz. So we have to go for the higher frequencies. Maybe it is 30 to 30 gigahertz in millimeter wave communication. That's why nowadays the millimeter wave communication becomes so popular. So in the higher band above 30 gigahertz, we can plan for higher spectrum. Now, what are the challenges? Challenges definitely signal propagation very differently. Design also, we have to design new hardware for the higher frequencies. Okay, so what we have observed, maybe 10 times densification, 20 times spectral efficiency, and 5 times more spectrum. With those, we can achieve 1000 times capacity of the current wireless communication scenario. So today, specifically, I'll be concentrating on how this spectral efficiency can be improved. Am I audible properly?
Yes, sir. Yes, sir.
Okay. Now, let us see the development of different generations of wireless communication, though it started from 1981 when it was only providing analog technology. In 1981, 2G was introduced, which little bit digital technology was introduced. And then internet in your phone, it was introduced in 3G at 2001. And in 4G 2010, mobile broadband was introduced, and 5G 2020. It is more faster, 1000 times more data. more robust and energy efficiency. But in today's talk, I won't be considering this energy efficiency part. But if you notice, almost 10 years it took from 1G to 2G, 2G to 3G, 3G to 4G. So what is beyond 5G? I'll come later on. Though I have talked about improving cellular network, there may be two tier of network. One is hotspot tier and another one is coverage tier. So hotspot tier, basically high cell density, short range per cell, wide bandwidth in millimeter wave band, spectral efficiency less important in this case. And in the coverage tier, provide coverage, elevated base station. Basically, the base stations, or maybe you might be noticing antennas will be put in a very high mast, maybe top of a building with high mast. So outdoor to indoor coverage basically operate less than 6 GHz and high spectral efficiency is desired. Okay. So again, capacity or throughput that depends on cell density, available spectrum, and spectral efficiency. Now, how to increase spectral efficiency? Because as per the Shannon's capacity of a channel is basically depends on this formula log of 1 plus SNR. So this part is basically SNR. So how to improve SNR? Okay. Now, issue is data rate. If we want to increase double, it requires 7 times more power, and that is not possible in this single antenna system. Instead of that, if we provide parallel transmission, spatially separated, maybe same frequency can be used for communication for this user 1, user 2, and many more. So this way, we can, by adaptive beamforming, we can improve the spectral efficiency. So let me consider this scenario where, let it consider this geographical area. It is represented along this axis, and this axis. Let it consider X and Y, and this Z axis we have represented the spectral efficiency, which is measured in bits per second per hertz. Now from 0, it is 500 to 1 kilometer along this X axis. Even along Y axis, 0 to 1 kilometer or 1000 meter. And 1 by 1 kilometer, let us consider we have put 4 base stations. And near the base station, you will get, if someone using mobile very close to the base station, you will be here having very high spectral efficiency. But if the user start away from this, little bit away from this, you will be here. The spectral efficiency is so low here. When he is very close to the base station, high spectral efficiency, and little bit away from, you will be at that null position. So how much we can put to the base station? Again, when he will be close to another base station, then he will get high spectral efficiency. And when he is away from that, again he will be in the null position. So that top view is represented here. So once the mobile user is very close to this base station, high spectral efficiency. Away from that, very low spectral efficiency. That happens basically the scenario when the user is near to the boundary, cell boundary. So where he may get very low spectral efficiency. One solution that is represented in the right side diagram by densifying in the top view, if you notice, we have increased the number of base stations. Okay, so you will get very good spectral efficiency at the peak. But again, maybe within very short distance, he can get very high spectral efficiency. But in between that, again, there is a deep fall in spectral efficiency. So densifying is not a proper solution, and you will get a mediocre performance at most places. Though you will get good performance at this blue point, but most of the white performance or white zones, you will get very low performance. So cell densification is not the solution. Higher frequency make it worse. Okay. So what should be the actual requirement? Requirement, instead of these small dot, if we have a bigger circle here, and one circle may overlap circle. So like that, here we have presented. So here in the right hand side, instead of a peak, if we have a wide zone, so throughout this wide zone, one can get very high spectral efficiency. So even there is only maybe very few areas where the user will get very low spectral efficiency, and most of the zone you will get a higher frequency. So we need actually such kind of development where we will get such kind of spectral efficiency. So what we desire? We desire strong signal but with same interference level. How it is possible? As I told earlier, beamforming is one of the solutions. So here in 3 diagram I have represented the first case, the signal variation I have represented here. The color indicates the path loss in dB, and M is basically representing the number of antenna in base station. So first case is M equal to 1, second case M equal to 8, and in third case it is M equal to 64. Now if you notice the first diagram, it is illuminating almost in all directions. So but usually is from that, as it is illuminating in all directions, it will die out very quickly, because as you know, the signal is basically, the received signal is basically inversely proportional of the square of the distance. As it is illuminating in all directions, before reaching the user, it may die out also. And along with that, as it is having very wide beam, it will create interference for the other user. Okay. Now, if you consider the second one, having number of antennas 8, the beam little bit narrowed and it is little bit directed towards the user. So now user will get better signal and his signal to noise ratio will improve because of this main lobe, though these side lobes will create interference for the other users. Whereas in the last case, when the number of antennas are 64, and it is basically a laser-like beam, only it is directed towards the intended user and it is not interfering to the other users. So main lobe focused at the user, narrow beams like laser, and array gain 10 log 10 m dB. So as we increase the m, the gain will improve and less leakage in undesired directions. Okay. So let me consider one scenario where one antenna or maybe one transmitter system having antenna and it is illuminating maybe with a wide beam with 60 dBi gain. Let it consider some user, we call it, these are the lucky user because they have LOS communication with the transmitter. So as they are lucky user, they are getting very high signal, but everybody is not lucky. It may happen also these user, they are the unlucky user because they are blocked by so many big buildings. So there is no provision of any LOS communication between transmitter and receiver. Only one way is non-LOS communication. That is, this beam will be reflected from this wall and it will come to the unlucky user. So fixed beam forming only helps lucky user, not the unlucky user. So what we should do for the unlucky user? Adaptive beam forming may be one solution. So let me give you some mathematical expression for this MIMO technology, multiple in and multiple out. So these a limiting factor of the capacity of the cellular mobile system is interference from the co-channel mobiles in neighboring cells. Adaptive antenna technology can be used to overcome this interference by intelligent combination of the signals and multiple antenna elements at the base stations. So in a phase array, a set of antenna elements is arranged in space and output of each element is multiplied by a complex weight and combining by summing as shown in the next figure. So let me explain what they want. So let it consider the receiver. This is the block diagram of the receiver and it has 4 antennas. So through one antenna, it is receiving some signal. Through antenna 2, it is receiving some signal. Through antenna 3, it is receiving some signal. And antenna 4, another signal. Whatever they are receiving through individual antennas, these signals are basically multiplied by some multiplicative factor W1. So the antenna 1 signal is multiplied by W1, antenna 2 signal is multiplied by W2, and so on. So after multiplied this signal, this let it consider this one X1, X1 W1, and then X2 W2, X3 W3, and X4 W4 will be combined here to get the actual output of this signal, of the combined signal. So let me explain, considering this scenario. Here we have considered two transmitter, and they are transmitting two symbol, or let it be signal S1 and S2. And on the receiver, this is the receiver block diagram as a whole, where we have two antenna, this one X1 and X2. Now the S1 signal may reach X1. Similarly, S2 signal may reach X1. Similarly, S1 and S2 again may reach to X2, but with different fading factor. So let it consider S1 reach to X1 with a fading factor alpha 11. S1 reach to X2 with a fading factor alpha 12. S2 reach to X1 with fading factor alpha 21, and S2 to X2 it is alpha 22. So what we receive at X? So X1 we receive S1 into alpha 11 plus what? S2 into alpha 21. So X1 is nothing but combination of X1 alpha 11 plus S2 alpha 21. And the whole X1 will be multiplied by W1. So this W1, it is with you at the receiver, you can adjust the W1 value. Now I'll show you that why, if this is our receiver, it wants to see or listen only S1, we can change the values of W1 and W2 because it is in your hand at the receiver. By varying the values of W1 and W2, we can either fix to listen S1 or S2. Depends on your requirement. Let's see. As I told, if you do remember, so Y is basically combination of two signals multiplied by this factor, because W1 is like a screw. So this weight you can fix W1 at X1 and W2 at X2. Now, as you do remember, the X1 is nothing but these two terms. If you do you remember that one? And I have taken common S1. So if you simplify this equation here, so X1 is nothing but S1 alpha 11 plus S2 alpha 21, and X2 is basically S1 alpha 12 plus S2 alpha 21. And if you take common, first multiply with W1 with X1 and W2 with X2, and then take common from this expression S1 and S2. So this equation Y equals to this. Now what do you want? If you want Y should be equal to S1 only, so what it should be then? So this factor should be 1 and this factor should be 0. Now we have now two linear equations. This is 1 and this is 0. Now from these two linear equations we can solve the values of W1 and W2. So if we have the W1 and W2 value, so Y should be equal to S1. And if someone wants to listen to S2, if Y equal to S2, then this factor is 1 and this factor is 0. Again, we have two more linear equations. From that, we may have different W1 and W2. By changing the values of W1 and W2, you can listen to either S1 or S2. So this is the idea. So just varying this W1 and W2 at the receiver, you can listen to this mobile or this mobile. Is it clear? So I have explained in the next slide this one. So if Y equal to S1, we have these two linear equations, and from that we can get the values of W1 and W2. And if Y wants to listen to S2, then this factor should be 0 and this should be 1. And then there will be different W1 and W2 value. Is it clear? And for simplicity, we have considered only very small unit of maybe 4 antennas. Now this can be formed into matrix form, okay, where this A basically defines the fading factor and B depends on which transmitter you want to listen. And from this equation, we can find out the values of W. Now here I did not consider the noise. So if you include the noise, then this equation becomes this. And from that, you can find out the W. So basically, how you will get benefit. So it is like that. The base station may have several antennas and it can activate few antennas toward one direction and another antennas to another direction. So this is basically adaptive beamforming and known as space division multiple access. Okay. So our group, we have done similar kind of work and it is published in John Williamson's. Now, as I talked about this MIMO technology, but it is not new. It is very old technology, even late 80s or late early 90s. You find a lot of articles in this paper. They have talked about this MIMO technology. Basically, they use this HC SDMA, which was also introduced in long-term evolution LT. Also, this standard 802.11 AC in Wi-Fi. But actually, this MIMO performance was not at all at the acceptable level. There are some reasons because the MIMO, they use only very small number of antennas and insufficient channel knowledge, a lot of interference, and few users to multiplex. So MIMO experiments in 90s and 2000, a deployment, very few deployment, no commercial success, and some negative experience about the MIMO during the time. It is only used for voice communication using circuit switch, and it was idea that it is very difficult to develop the hardware, and communication theory was not available during that time, and number of antennas also very, very small, fairly small. So it did not get much success. But the motivation about this MIMO is the data rate grows with increase of antenna, that is M and user. So here in one experiment, it is shown the spectral efficiency along y-axis and number of users along x-axis, and it has considered this Rayleigh fading, independent identical distribution Rayleigh fading. And if you notice, there are 4 measurements where this one graph actually is representing M by K ratio. For the first graph, it is M by K equal to 1, whereas the second one M by K equal to 2, the third one is M by K equal to 4, and for the fourth one M by K equal to 8. So if we consider this case, say number of users is 10, for this one, the number of antenna M is also 10 because M equal to K. Now, if we go above, here for the 10 users, the number of antenna 20, and it is improving in spectral efficiency. For M equal to 40, again spectral efficiency improves. So M equal to 80, when M by K ratio is 8, again spectral efficiency improves. So one thing it is observed that from that graph, if the M by K ratio is improving, the spectral efficiency can be improved. Am I audible and visible properly?
Yes, sir, it's visible, sir.
Sir, visible.
It's visible.
So far, we have talked about that massive MIMO, but let's let me try to give you some idea about massive MIMO. Massive MIMO means massive in number of antennas. So basically main characteristics is many number of base station antennas where M equal to 200 antennas and K may be only 40 single antenna user. So this, in this case, maybe M by K is 5. So if we improve more this M by K ratio and this antenna, at least it should be more than 64, then we call it this system as massive antenna system, massive MIMO system. So key here is greater K. And it can produce very directive signal, little interference and leakage. So spectral efficiency grows with number of users. Okay, if it can provide many number of users, so spectral efficiency data rate will be high and spectral efficiency always will be high. So this actually the massive MIMO idea, it was introduced by Thomas Margetta in his paper in 2010, where he has mentioned non-cooperative cellular wireless with unlimited number of base stations. But during the time, it was not in reality. What he has proposed, some science fiction idea he has proposed in his paper, and it was published in IEEE Tangential Wireless Communication, and he got this prestigious award in 2010, 13 and 2015 too. Excuse me. Now, why that MIMO, the 90s MIMO now achieved some goal even in reality in 2020. Nokia's massive MIMO system is commercially available. Why? Because for last few decades evolution of analog beamforming. So here I have compared with some different antenna systems here. So single antenna system, maybe this one, it is having 8 small elements, each having 7 dBi gain. One transmitter transceiver chain, fixed beam 16 dBi. Whereas same panel may be combined 4 such panel. And what it can produce, it is having 8 antennas or 64 elements, 32 per polarization, 8 transmitter chain, up to 8 horizontal beam, means 8 horizontal beam it can control, but still it cannot control vertical beam. So here it is having 64 antennas. It is called massive MIMO antenna array, 64 elements, 64 transceiver chains, and up to 64 3D beam it can control horizontally as well as vertically. So Thomas Margetta, he says, channel information is not everything, it is the only thing, because you need to know where to point the beam. From the antenna, you have to know where the user is lying. So user's location has to be available in the base station. So how it can be done? Give strong signal, receive signal, limit interference between users. So conventional approach is like that. There may be a 8 antenna system, and 8 antenna will be illuminating or sending some pilot with some angular beams, and the receiver will give some feedback, or user reports the feedback to the base station that this one is the good out of this. So they should send the SNR label or that information they should return to the base station. Okay, so this is one way of that. This is conventional approach, and this possibly good thing is that both TDD mode, but means time division duplex, and frequency division duplex mode, both it is operational. But bad thing is that it works only in line of sight and single user transmitter. Whereas in case of massive MIMO uplink estimation, here only user sends the pilot to the base station, and among the signal, base station estimate where the user is, and accordingly it can send or control the beam. But its bad thing is it does not work in FDD mode. It works only in TDD mode. So let me explore more. So the first mode, if it is having 8 antennas, m number of antennas, so m antennas, m beams should be transmitted from antennas, and out of these the user may be on the 4th antennas. So from that user, the station will get the information from the user, and then accordingly he will control the beam towards the user. So what is bad thing? Now if m is very large here, instead of 8, if it is m equal to 200, then it is very difficult to maintain large number of pilot signal. Whereas in the other case, only the user send towards the base station. But the negative point is it does not work in FDP mode. Okay. Now, as from the beginning, from the conventional antenna system to MIMO system, then massive MIMO system, and we have talked about, then massive means what? Is it massive in size? So basically, it is massive in number, not massive in size. We have compared two systems, the conventional system, a Catherine 8001061 system with 16 dBi directivity. Its height is huge and width is around 154 millimeter and 70 millimeter. Whereas today's this Ericsson AR646864 antenna array, which operates on 2.5 gigahertz band, and its height is around 1 meter, and length and width 520 millimeter and 187 millimeter. It is well comparable with this single antenna system, and weight also 6.4 kg, carrier aggression 3 into 20 megahertz, and power 40 watt per band. Now, does massive MIMO, what it was claimed in the theory, the literature, does it work same in reality? So, to justify that, Professor Emil Bronson and his group, they performed a hardware simulation in the city of New York. So, what they have done from this paper in 2019, what they have done, they have fixed a massive MIMO system, and they have put in different building 16 cell they have considered, and 9 user per cell. So they have used 3.5 gigahertz band, 20 megahertz bandwidth, 43 dBm, and state-of-art processing. Okay. Now what they observe, so they have considered two arrangement of antennas. One is planar array, another one is linear array. So planar array, it contains 24 into 8 elements and length 1 meter by 0.34 meter. Whereas linear array, 24 into 4 means almost 192, not almost 192 element. Whereas in linear array, it is having 192 element, having 8 meter and 0.04 meter in width. And they compared with Marjeta baseline Rayleigh fading. So Rayleigh fading, whatever they have proposed, that is in theory, but in reality, it may not be same. So what they have done in the experiment and they have observed, so they put the downlink throughput per user in megabits per second along x-axis, and along y-axis they have took that cumulative probability distribution, okay, along y-axis. So what they noticed, for the lucky user, there is not such difference with the theoretical one and with the planar or linear array. Almost all are same. But in case of unlucky user, if you notice, the linear array is clear winner here. So here, which one is the linear array? This one. Okay, so it is the clear winner. But how it is possible? Linear array, it is 8 meter long. If you put two, if you just increase the width into 2, so still it will be reduced to 4 meter. So still it is a huge length. So it is not easy to deploy all these things. Linear array. Now, let me give you some idea. So this is the conventional approach of single antenna system where it has 3 sectors. Now, with this massive MIMO, in one sector, we can incorporate 192 antenna. Instead of 3 sector antenna, these places can be replaced by this 192 antenna array. Okay, so basically this is, we can call this first generation of massive MIMO. Each antenna element becomes digitally separable, massive in number, 64 input output instead of 8, not massive in size. And it requires spatial multiplexing. Okay, and which requires digital beamforming. How to implement beamforming? Same signal from all antennas and vary phase and amplitude per antenna, so vary phase and amplitude per subcarrier. So this digital beamforming is the future. There are another alternative approach of hybrid beamforming, but that is not possible to for this purpose, spatial multiplexing. So digital is the future. Now, how big can massive MIMO get? So massive MIMO delivers extreme spectral efficiency, no theoretical capacity limit, goes towards the infinity as the N increases. So you increase number of antennas if you require high spectral efficiency. But practical limit, 100 antenna arrays not larger than in 4G, increasing cost of deployment of base stations and distributed deployment in the future. So it may not be one antenna at one base station, it may be distributed throughout the geographical area. Now, whatever be the scenario, in this paper they have talked about in 2018, in near future, such kind of fully digital massive MIMO will be available, commercially available, where it length and width 25 into 20 and height may be 30 centimeter. By NEC Corporation, they are designed this one and with 24 elements, 15 elements each, and digital and adaptive horizontal beamforming. So it will be available commercially in very near future. Now, let me talk about some world record in spectral efficiency. 2 groups in Bristol and Lund University in 2016, they have jointly claimed that they have achieved world record in spectral efficiency, that is 145.6 bits per second per hertz per cell, with 128 base stations and 22 single antenna systems or users. With the modulation is too high, 256 QAM, with 20 megahertz bandwidth at RF 3.5 gigahertz. Though they have done, and that is available in this website, the video is available. But is it practical? Is it possible to introduce so high multiplexing technique, a modulation technique? So the Professor Emil and their group, they conducted such kind of simulation, and what they observed, and they have done the experiment with 500 base station antennas, and what they observed, getting this 145 spectral efficiency with 120 base station is not possible. See, if you see 128 base station, how much they can achieve? Maybe only 50. But it is possible to achieve in reality also this so high spectral efficiency, but with the cost of more number of antennas. Okay. So 5G is more than broadband. It is basically 5G is for Internet of Things. Wirelessly connected society, machines, vehicle, everything gets connected. Other use cases than mobile broadband. There are 2 use cases. One is link reliability and second one is massive machine type communication. So for link reliability, connected factory, robots, traffic safety applications, etc., even ultra reliable low latency communication systems. For massive machine type communication, many low cost sensors and actuators deployed everywhere. Maybe this one 50 billion devices. Sporadic transmission battery should last for 5 years. Now, can massive MIMO play an important role here? The 2A it can get benefited. One thing is range extension. With the same power but having more number of antennas, it can get extra range, as this capacity is 10 log 10 with M. So if you increase the M, you can get extra range. Or if you don't increase the power, then it should be low power devices, so battery life will increase. Okay. Now let me consider one scenario of IoT system. So let it consider for single antenna system. Normally it support maybe say maximum maybe tens of kilometers, and we assumed this one is 150 dB path loss. Now let it consider the transmitter transmitted power 20 dBm plus antenna gain 2.15 plus receive antenna gain 2.15. Then path loss we have considered for a IoT case, maybe post case 150 dB, and then noise power minus 120 dBm. So it is coming around minus 5.7 dB, which is enough to support these IoT devices. This is sufficient for binary modulation with repetition coding, transmit a few data packets per day, and it is possible. But if you increase the number of antenna to 100, it will increase the ACNR by 20 dB. So it will improve the link reliability. Even you can reduce the power to 10 dBm. Instead of 20 dBm at the transmitter, we can reduce the power, which may increase the battery life of the system. So massive MIMO for 5G mobile broadband applications, very high spectral efficiency, multiplex many users, great improvement at the cell edge. Basically, I started with that concept. Maybe close to base station, there is no problem, but when it is away from the cell towards the edge, that time it faces the problem. But here, great improvement at the cell edge. Ultra reliable, low latency communication, channel hardening, elevated scale, small scale fading, fewer retransmission required only, more predictable performance, massive time communication, extended coverage, more cost efficient deployment, reduced transmit power for battery power devices. I have taken this from this paper. Now, we are here at the 5G. So what about the beyond 5G? Now, maybe from next 5 years, we can carry out the basic research and inventions beyond 5G. And from here 25 to 30, we can standardize the 6G applications, because still it is not standardized yet. So which issue will not be solved by 5G and what is needed beyond 5G, that we can fix in coming years. Now, what are the 5G, 6G applications? Though we are talking about 6G applications, but we are not still aware of what are the 5G applications are. Though it was proposed, 3G was proposed or introduced in 2019, but the applications, these are the believed 3G applications, it was available. If you notice, broadband internet, it was available in 2008, and video calling, FaceTime in 2010. So almost it took 10 years from 1998 to 2008 or 10. So almost it took 10 years of time in reality to available all 3G applications. So nowadays all papers they're talking about 3G applications are just speculations. Okay. Now, so what we can do, we start from setting some performance matrices for 6G. It may be peak data rate 100 Gbps to 1 terabytes per second, very low radio latency, high battery life, many more devices, means more densifying with more devices, traffic increases, and outage may be very less. Again, one more important thing, more energy efficient. Also, this positioning we have to improve. And all these parameters, though I have taken this one from this image source flagship 6G flagship in 2019, but all these we cannot fix together. So we have to go one by one. We must look for the new solutions which can improve 10x improvement. Maybe data rate will improve 10x. That technology we should see in future. If you notice, as I mentioned, Thomas Margetta, what he told in his paper in 2010, that was basically a science fiction idea, and he has theoretically presented in his paper, massive MIMO concept in 2010. But if you see, in 2019, it is commercially available by Nokia. So this is the massive MIMO system. Now it is available in 2010, 2020. Now let us consider which science fiction idea from 2020 will become reality in 2029. We can think such a way, so theoretical design can be done, and maybe in 10 years, next 10 years, it will be commercially available. Like for massive MIMO, the spin, they claimed they deployed 1,000 sites in 2019, 64 antenna systems. So what is next? In my lecture, I'll highlight about few important open research areas, that is meta surfaces and holographic beamforming. Meta surfaces also known as intelligent reflecting surface. Along with that, I'll talk about the cell-free concept, cell-free network. Cell-free network means cell-free network, intelligent reflecting surface, and another one is extremely large aperture rays. So if you notice, there is also a limit increasing a huge number of antennas in massive MIMO system. Now here we will introduce a new term. Instead of having the active element, we can put some passive element in between transmitter and receiver, and which will help to improve the signal level. And before that, let me talk about the cell-free network. It is like that, instead of having that cellular architecture, any user can move anywhere in the geographical area, and combiningly many antenna will be helping him to provide the service. Am I audible properly?
Yes,
Hello?
sir, you're audible. Yes.
Okay. So one approach was initiated, which is known as coordinated multipoint transmission. What it does, instead of having one antenna responsible for one user, can we combine them? So a cluster of antenna system, a cluster of cell, where maybe 3 base stations will be there, and combiningly they will be providing service to the users. Because in this case, maybe cell, when the cell is very close to base station, there is no more problem. But when the cell reaches to the boundary, then it feels a lot of problem because of the cell interference. So cellular with cooperation cluster, coordinated schedule, coordinated spatial beamforming, joint transmission to one user. But it was not a successful solution. A lot of backhaul signaling required between the APs, between the base stations. APs communicating each other. Instead of that, a massive number of antennas can be deployed in the geographical area, and all the antennas will be connected to a central processing unit through some cables. And right side, I have represented that one, the cell-free network. So massive number of distributed antennas, short distance from user to some antennas, connection to massive MIMO. Again, we have to maintain this parameter. Number of antennas is greater than the number of users. So instead of dividing the area in different zones, distribute the APs or base stations over the whole area. The APs are connected with CPU with front hole cables, collaborated AP serving together all the users. So maybe one user is here, the nearby two base station will help them or him. But here also one problem is there. I'll come to that problem later on. But these two approach, this is coordinated multi-point approach. It is basically network-centric design, whereas the cell-free approach is each user served by the all APs in its area of influence. It is called user-centric design. Again, Professor Emil, they have conducted one experiment for the cell-free architecture. They have considered a cell 1 by 1 kilometer with 400 antennas and 40 users. 3GPP Arbon microcell model they have considered, uplink to 20 megahertz bandwidth and 100 milliwatt power. So they have considered these two setup. One is cell-free approach and cellular setup. 4 APs on the square grid. So they have divided the system with square grid and they have put this 4 antenna with centralized control and also distributed control. Whereas this cellular approach, the 4 APs having 100 antennas, small cells, and what they observe, so they have plotted the cumulative distributed function along y-axis and along x-axis it is spectral efficiency. And what they observe, the cell-free centralized approach is the clear winner. So this having a very high spectral efficiency for most of the cases. So me and my group also similar kind of work we have published, not exactly cell-free approach, but no beyond the cell boundary. We have work done in few papers and it is published. Now, what is the problem in the practical convenience? So once antenna is defined, again, in future, there will be requirement of another antenna to deploy here. Again, it should not be connected to the central processing unit with a separate cable. Rather, it should be connected with the nearby base station. So it is like that. And see, this can be possible maybe with the new invention of radio strip antenna system. So radio strip antenna, the concept is like that. Why these cables will be connected to the CPU, only the passive cable? Why not this cable should act as an antenna? And that is possible with this new architecture of radio strip antennas. So if you notice this one, the central controller it is having, and it is having within a maybe 1 meter of length, having so many antenna elements. And it is possible at 10 gigahertz, this 1 unit of dual polarized antenna system, whereas in 28 gigahertz, same 4 unit can be possible. And with the higher frequencies, more unit can be possible. And it is available with this Professor Emil, and the video also available in the net. So same radio strip antenna implementation. And what they propose, they maybe in factory or cultural places or any shopping complexes, wherever the passive cables are there, they should act as an antenna system with the radio strip implementation. And with this use of the radio strip antennas, you may get the performance like that. What we propose in the beginning of my presentation, we should have a good spectral efficiency if it moves from one cell to another cell. The second important open research area I should mention here is that intelligent reflecting surface. Again, very, very interesting topic in beyond 5G. So idea is basically a reflecting surface, like when a incident wave falls on a reflecting surface like mirror with a angle, incident angle theta I, and it reflects back or scattered back with a angle theta s, and you will get strongest signal when theta I equals to theta s. Now this IRS or intelligent reflecting surface, it mimics what the mirror does, but in a controllable way. So here the reflected signal is scattered in a particular direction, but here the having a surface having so many elements, and it can control the beam, and which can be installed in between transmitter and receiver. If the transmitter and receiver in between there is a blockage and there is no noise communication, still these can be used to control the beam towards the receiver. So there are so many alternative names: software control metasurface, reconfigurable intelligent surface. How it works? So basically, it is the idea is very old idea: reconfigurable reflect array or metasurfaces. It is also known as software control metasurfaces, real-time software control metasurfaces. So in between a transmitter and receiver, a metasurface can be put, and these units, the small element on the surface, it can control the beam towards the user. One beam, maybe one user can be controlled towards the one user one, another beam can be controlled towards the user two, and so on. So people are giving different kind of names: software control metasurfaces, or reconfigurable intelligent surfaces, intelligent reflecting surfaces, added wireless network, and so many new names. So two important perspective cases here: one is energy focusing and another one is energy nulling. Like there should be one controller which will be controlling these elements towards the desired user, or it can nullify for the undesired user. So here it may be constructive interference, and in the second case it may be destructive interference. So here it will be SNR will be improved, and this in this case this red signal won't be interfering user 2. So this idea is basically originated from the reflect array antenna. A microstrip reflect array antenna consists of a flat array of microstrip patches or dipoles printed on a thin dielectric substrate. A feed antenna illuminates the array, whose individual elements are designed to scatter the incident field with proper phase required to form a planar phase surface in front of the aperture. It means a transmitter transmitted the signal towards the aperture, and you design the aperture as per your requirement. You want to focus here, accordingly you design the aperture. So this is the photograph of this reflective surface, and it is 6-inch reflect array with 22 by 24 element, total 522-28 elements, and its signal measures and calculated as represented in this diagram. Now, one more thing I should mention: what should be the size of the meta elements? Now, if you notice, if it is size of lambda or 2 lambda or comparable to lambda, then it's scattered mainly as per the theta I equal to theta s. But if we have the meta element size in order of lambda by 5, then you can control the beam towards the desired direction. So how it can work? Just let me discuss the mathematical expression. So here the transmitted signal. So in between the transmitted signal and the reflector or the IRS, the channel is Gn. We have considered the nth element. Then there is a phase shift e to the power j theta n, and again from the element to the receiver, channel is Hn. So end to end channel is Gn multiplied by e j to the power theta n multiplied by Hn. Now if the signal is x, the signal should be multiplied with this element. And if there is capital N number of element, it should be summed up. And then the noise part should be added to get the received signal while. So what should be the channel gain? So for this transmitter to IRS, the channel gain is A by 4 pi dg square. The distance is dg from transmitter to the IRS, and from the IRS to the receiver, the distance is dh. And the area of the element is A. So channel gain for this channel is A by 4 pi d square. So end-to-end channel gain, if you combine both, so it is A square by 4 pi dg dh whole square. I have taken from this paper. And for the end-to-end channel gain with n element, so this term will be multiplied with this term, where capital N is the number of element in the metasurfaces. How much time I have?
Sir, you can have another 5 minutes of time, sir. It's already
Okay.
you can have
So,
another.
yeah. Let me just explain this one. So they have Professor Emil has conducted one experiment with this transmitted to IRS minus. This is the channel gain minus 75. This is also minus 75 gain, and he has plotted the spectral efficiency with the number of elements, these passive elements. What they noticed, when the direct path is available, there is no more improvement in the gain, in the spectral efficiency. But when there is no LOS available, then there is a huge gain in spectral efficiency with a huge number of elements. And how to send the pilot, I am not discussing here, but very important thing, where to place the IRS. So they have done one experiment. They have considered 50 meters distance between the source and destination, and from the source 5 meters apart, and with a distance of D, they have put the IRS, and in between they varied the D, and they have calculated the total channel gain, and it is plotted in the graph. What they noticed, the total channel gain is high when they close to source, or maybe when close to destination. So in between there is very less gain. So why not to put the IRS at the transmitter? What is the problem if they are co-located? So this concept is known as holographic beamforming, where a RF generator is just put just behind the IRS. So what they have got advantage? No path loss between RF generator and surface, and thin form factor invisible deployment, ideally contiguous surface. And already it is commercially available by Pivotal Comier. They have designed this device of this holographic beamforming device or metasurfaces with 28 gigahertz small array and one RF chip. In future, maybe with more RF chip, it will be available. So our group also done a small work on IRS, and it is published. And these are my references. And thank you all. So can I stop sharing my slide?
Yes, sir. Yes, sir. Thank you, sir. Thank you for your wonderful session. It was very interesting, sir. We have gained a lot of information regarding meta surfaces. Thank you very much for that beautiful presentation, sir.
Okay. Thank you. Thank you all.
Can I raise a question, sir?
Yes.
Sure.
Sure. So I cannot see anybody. Am I visible to you?
Yes, sir. You're visible, but participants would have turned off their video. That is why you will not be.
Okay, but okay. Yes, question please.
Yes. Sir, good afternoon, sir. So I have a question like, sir, this massive MIMO and array both are same, sir, or they are different?
No. The massive MIMO, if you concentrate my lecture, I started with single antenna system, then many number of antennas, multiple antennas, then they increase the number of antennas at the transmitter as well as the receiver. Those are basically active elements. But these metasurfaces, it is placed basically in between transmitter and receiver. The third case I did not discuss, even people are considering to put a huge metasurfaces, extremely large metasurfaces. Maybe it can be placed in a building. Like if you notice earlier days, the people used to put relay to boost up the signal. You can consider these metasurfaces is one kind of relay kind of things.
Okay, so sir, like first single element, next array. Can we go like in this chronology, sir? Like single element, next 2 by 2 or 4 by 4 or 8 by 8 as an array.
Yes.
Next, we can go for a MIMO.
Huge number of antenna.
Huge number of array falls under massive MIMO.
Yes. When the number of antennas greater than 64, I have mentioned, you can call it massive MIMO, which was introduced by Thomas Margetta. And what he claimed that increasing number of antennas capacity, channel capacity may be improved.
Yes,
But
sir.
you cannot improve or increase an infinite number of antennas. So then question comes, beyond 5G, people are doing research, why not to put some reflector over there? And if the people who studied the rake receiver long back in 3G, similar kind of concept, maybe here, though it is passive element, but it has some capability of controlling beam. It basically the surface, it is having in between two metasurfaces, there will be a varactor. By changing the voltage of the varactor, it can control the phase of the beam. That is the idea. And
So
now it is, yes.
So normally 5G has a problem, the major problem, like when the obstacle is present almost at 10 units.
Yes.
So for that, how we can we say that this meta reflector, that the intelligent reflector surface is a solution for that? Can we explain it?
See, actually, if you notice in my presentation, I have told the father of this Massimo what he proposes theoretically in 2010.
Is
Though it was
2019.
it is like a science fiction idea, but now it is available commercially.
Yes,
So who knows, in 2030 it will be available in the market also commercially.
okay. Thank you, sir.
Yes, sir. Thank you so much, sir. And we have one final question, sir.
Hello.
Yes.
What is the basic to design a massive MIMO? Is
No.
measurement of massive MIMO possible anywhere in India?
See, that again you have to combine with those antenna designers. But in the world, as I have told this Professor Emil, they already shown with the collaboration of Ericsson. I did not show those slides. So already in collaboration with the Ericsson, they already designed this massive MIMO system. Even Nokia, I given the picture of Nokia, the massive MIMO system is already available in the market.
Hello.
Yes.
Excuse me, sir.
Yes.
Sir, if you are using S1 and S2, sir,
Yes.
is it audible?
Yes. You are audible.
If you increase in the S1 to SN, how to calculate the complex weight and how to reduce the SNR, sir?
Which one?
How to calculate the complex weight and how to reduce the SNR, increasing the S1 to
Yes.
SN.
That
SN.
one, if you go through that mathematics, I have told, considering only two signals, S1 and S2, and S1 signal is multiplied with the fading factor, because the channel I did not consider a Rayleigh channel. A very simple fading factor I have considered. The factor is alpha 1,1. So that signal with that fading factor, it will reach to the receiver to one antenna. Similarly, to that same antenna, several signals maybe from the S2 with different fading factor, maybe alpha 2,1, reach to that, and it will be combined. And on that combined signal at the receiver, they are putting some weight factor. And if you do the mathematics, and from the another antenna, if you combine and do the mathematics, y equal to what? Y equal to W1 S1
Yeah, alpha 1,1. And,
now, if you want y equal to S1, then the product with S1 factor should be 1, and the another one S2, the product of those terms should be 0. So we have now two linear equations, and from those two linear equations, we can find out the values of W1 and W2. A very simple example I have just shown you, though I have taken this one from antenna book. Any more questions?
no, sir.
I could see two more participants have raised a question. Raise your hand to ask a question. You can post your question, or you can directly ask, sir. Any more questions, participants?
Sir, in MIMO, we have different frequencies, sir, or they, as in the case of array, same frequency
See,
we have?
yes. Theoretically, if you notice, that is the way I have mentioned, the same spectrum can be used for the other beam. So that's why it is called space division multiplexing. Using same frequency, you can use for the different user using same frequency. Why? If you have very narrow beam, so this beam won't be interfering with the other beam. There is a very less chance of interference. And if we can maintain some orthogonality between those signals, then there is no problem at all. Definitely it is same frequency.
Yes, sir. Thank you so much for the wonderful session, sir.
Okay. Thank you all.
Sir, we would request you to just stop your screen sharing so that we can have a group pic with your video on.
Okay. I think I have stopped, but it is not showing anything. Okay.
Yes, sir.
Now I am visible, no?
I would request all the participants to turn on your video so that we can have a group pic of the session. Yes, sir. Thank you so much for that wonderful presentation, sir. Very informative session. Thank you so much.
Okay, thank you. So I can leave the session, no?
Yes, sir. Yes, sir. Thank you, sir.
Okay.
Thank you, participants, for your active participation. I would request all the participants to submit your feedback links then and there because you could see most of the participants are missing out feedback links. I would request everyone to be very active in the participation. So thank you very much. We will end for day. And by tomorrow morning, 9:30, we will have the session starts. Thank you so much, participants.